Okay, so SQL. Your basic SQL query has three parts: select from where, there is what is called the target list, or the select list, or the projection list. There is the from expression, or the sources, or the from clause. And there's the where clause. The from clause has a couple of different formatting options. The basic primitive for a from clause is a relation, and you can have a comma between relations. You can have r, and then the literal word join. You can have r natural join. Or you can have r join s on and then a condition. The first two behave identically. They essentially represent cross products. R natural join s. Does anyone want me to explain natural joins? Okay. Same attributes from both relations. R join s on some condition you can think of as essentially a actual join. R and s, and then you provide some sort of condition that is applied over R and S. In general, most database systems don't actually do anything interesting with this condition. They just treat it as part of the where clause. Okay, basics. The where clause, any Boolean expression over any of the attributes in the select, any of the attributes in the generated by relations in the from clause. The from clause can, what else? The select statement, there are two general flavors of select statement. There are flat selects and aggregate selects. So if the target clause is entirely single-valued expressions, then you've got a flat select. The other possibility is when you have a select that has a set of columns and a set of aggregate expressions, where the columns are just columns and the aggregates are something involved. Every one of these terms has some expression that includes an aggregate function such as sum of an expression, count of an expression, count of star, average, min, or max. There's also a group by clause. And the restriction that that the set of columns is a subset, a weak subset of the group by columns. Any more detail on aggregation? or at least on SQL for aggregation. I will get to one particular additional distinction in just a moment, but okay. Oh, and then so the other thing you can have in a select statement is order by or limit clauses. So the order by clause tells the database that you want the data ordered by some specific expression or column, either in ascending or descending order. And the limit clause limits the result set to a fixed number of outputs. And there's a couple of variants of that also allow you to pick more than just to start from a particular record and get only a few more. Questions so far? Okay. There's a significant distinction I want to make, and that's the distinction between max and argmax. So this has nothing to do with this distinction by itself has nothing to do with SQL or databases specifically, but the implication of the distinction actually is important. The difference between max and the mathematical function argmax is that max returns the maximum value, whereas argmax returns the index of the maximum value. So if I have a set, let's say I've got a data structure that's some map. 3, 7, 2, 5. If I call max of m, I get back a 7. If I call argmax of m, I get back 2, or 1, depending on, let's call this 1, 2, 3, 4. I get back 2. This is an important distinction because the aggregate function max in SQL is this one. You can do argmax, but it is going to require you to use an order by limit query. So if you want the tuple that has the maximum value in it, you need to use order by limit. If you want just the maximum value itself, then you can use regular max. rolling right along. So the last bit of SQL that I'm expecting you to at least be familiar with is the idea of nesting. So if I can take any select query and I can put it into parentheses, and then it becomes something that I can put into another query. There's three ways that you can do. There's three ways that you can nest a query. The first way is to treat the entire query as a relation. In relational algebra and SQL, there's no difference between a table that you have on disk and the output of a query. The output of a query is just another table, another relation. So you can take any select query and you can put it in the from clause, and the output of that select query becomes the input to the next select query. Key thing, or the thing that many people, one of the challenges many people run into is that each one of these from nested queries needs a name. The second type of nesting is single-valued expression nested queries. So I could I could put a select statement in either one of the target attributes or in the where clause. Of course, if I put it in the where clause, I'd probably need to use it as part of a comparison or something like that. Key thing here is that SQL semantics mandate two things about this nested query. The nested query can only have one attribute, and it must return exactly one row. Most SQL databases will not actually check to see if it returns more than one row until you actually run the query. So this isn't something the compiler will catch. If it returns more than one row, your query will just crash while it's running. And then the third type of nesting is relation nested queries. And this is used in conjunction with one of several comparators. In exists I'm blanking on the one other. It's in the slides. But the main point is that here you're still required to return exactly one attribute for in. You can return as many. But you can return as many rows as you want. The in comparator tells you that a particular value or attribute is in, the in comparator returns true if whatever value x is part of the return, the values returned by select. The exists operator tells you that there is that the nested select query returns anything. If it returns even one row, exists as true. That's what I'm missing. So there's the negation. So you can do not in or not exists. Questions? Yeah. That was a while back, but yeah. No, exists returns true or false. So exists and then a nested, both of these are Boolean expressions. You'll see them in the where clause, and exists returns will return true if the nested select statement returns anything. So if it returns even one row, the whole thing returns true. The other thing to mention is that both of the expression nested, either the single valued or the multi-valued ones, can reference variables from the outer expression. So in whereas a from nested the from nested queries are self-contained. They have to be queries that you can execute by themselves. If it wouldn't be legitimate SQL just in and of itself, then they're not. Then you can't put that in a from clause. Whereas if you have an expression a select statement nested inside an expression, then you're allowed to refer to columns outside of the select columns that are coming from the from clause of the outer query. Okay. There's also window queries. In the interest of time, since we covered that fairly recently, I'm not going to go over it again, but that's also on the list. Any other questions about SQL?
What is the point of the second nesting where you select a select? If the select already returns one attribute, why would you need another outer select if you can only also return that one attribute?
That's a great question. Why do you need a select in the target list? Nope. Time for some more paper. So, strictly speaking, you don't actually need it. It's a piece of syntactic sugar that makes one particular type of thing, one particular type of lookup easier. So let's say that I have two relations, R and S. And let's actually give them some schemas. So R has an attribute A, and then S has an attribute A, B. And let's also say that A is a key for S. So A uniquely identifies any row of S. So, let's say that I wanted to generate one tuple for every B in S. For every row of R, I wanted to look up the corresponding B. How would you do that? You join them. So I could write a join query. Select B from RS, where R dot A is equal to S dot A. However, I could also write, and this is almost entirely equivalent. Whoops. Right. So these are almost equivalent queries. For every row of R, I'm going to look into S and find the one row of S where S dot A is equal to R dot A from the outside. Now, this is a pretty straightforward example where it's pretty clear. I mean, these are completely equivalent query. Oh, it's not entirely equivalent. This is closer to an outer join. But so what happens if there isn't an S dot A that matches? So what if there's a 5 in here? This still returns null, give or take. But so they're not completely equivalent, but for the most part, you can think of them as being relatively close. The nice thing about this formatting of the query is that it keeps all of the lookup conditions together. So here I can very clearly see that these rows are coming from S. It also very directly implies this is a lookup. I'm dereferencing this foreign key. In general, you'll usually see this query getting converted into an outer join anyway in most database systems, so no big deal. But syntactic. I don't want to make this claim. I'm not going to stand by this claim, but yeah, I can't off the top of my head think of a good a case where this provides more expressive power than outer join. Okay, any other questions on SQL? Yeah.
If we used a view in the from as opposed to having the nested query, would that be more efficient, or would we?
If you used a view instead of a from nested query, would that be more efficient? Actually, interestingly enough, if it was just a view and that's it. So I'm going to start by saying that they're identical, and then I'm going to go and disprove myself. But in general, no. They're, this is exactly like defining a view and just saying stick it in there. The two reasons that a view might be more efficient. So by defining a view in some of the more advanced database systems, the system might actually go out and start gathering statistics to make it easier to optimize queries that reference that specific view. So the optimizer might have an easier time making the correct decision. The other thing is if you materialize the view, then obviously it's going to go way faster. Good question. In effect, that's what you're doing. Here, the reason that you would actually want to do this, the reason that you'd actually want to nest a query in the from clause, this actually does give you more expressive power. Because SQL has a very strict order of operations. First, you do the selection, then you do the projection, then you do the aggregation, then you do the sort. If you are trying to do something that requires you to operate on data after it has been sorted, such as if you wanted to, let's say, run a query over the argmax, or the top 5 outputs of a given table, then you'd actually have to use this. You'd have to pick the 5 out and then select from the output of that top 5 subquery. Onwards. All right, relational algebra. By now you guys are probably fairly sick of it. A bunch of operators: projection, selection, cross join, union, group by aggregate, and distinct. Set, bag, and list semantics being ever so slightly different. Main thing that I expect you to take away from relational algebra is comfort in manipulating relational algebra expressions according to equivalences. I'm not expecting you to memorize the equivalences. I usually have a lookup table on the exam, but I do expect you to be comfortable writing one expression into another. Also translating from SQL to relational algebra. Questions so far? All right, moving right along. Joins. So we talked about a bunch of different join algorithms. I expect you to understand how each of these algorithms work. We talked about nested loop join, block nested loop. We talked about hash join, what I referred to previously as grace hash join, and what I am now referring to as one pass or in-memory hash join, what I previously referred to as external hash join, and am now referring to also as two-pass hash join. And that's what the terms the textbook uses, one pass or two pass. Index nested loop join, sort merge join. For aggregation, in memory or one pass aggregation, hash aggregate, or using a hash function to do aggregation, using sorting to do aggregation. We talked about sorting in memory. Well, we didn't actually talk about sorting in memory because that's what your algorithms class is for. But we did talk about sorting on disk, and this funky two-pass sorting algorithm. Where in the algorithm we did one pass where we created a set of sorted runs, where each run was basically we took as much data as we could, sorted it in memory, dumped it to disk, then loaded the we have first data set that is in random order, another bunch of data random order, another bunch of data in random order, where each of these is the size of memory. So the first step, we take the random ordered data and we sort it. One more. And then we iteratively take the sorted runs and we merge them in memory. So because they're in sorted order, we don't have to load the entire thing in order to be able to merge them effectively. Just like sort merge join, we kind of iterate through the sorted order, and as we do so, we dump the records into a sorted list that's twice as big. We do the same thing repeatedly. Now we have two bigger sorted lists, and then we combine everything once again into one big sorted list. This is very quick, but I can go into more detail if anyone would like. Questions? On disk sort, yeah. The external, out of core, on disk, those are all terms that mean the same thing. External meaning outside of main memory. And out of core, I don't know why people still use the term, but way back in the days, there was core, what we refer to now as RAM was core memory, because it was made from iron cores that would store that would be magnetized. Work kind of like hard disks, except smaller. Okay. So algorithms. There are a bunch of join algorithms, a bunch of techniques for doing aggregation, mainly using hashing and sorting, and we talked about this external sort algorithm. All right, we also spent a bunch of time on data organization. We talked about a couple of different ways of laying out attributes in rows, either treating the attributes as being fixed size, using delimiters between attributes like in a CSV file, or using information in kind of a header chunk, a fixed size header chunk that told us how big each attribute was in that particular row. Then we talked about layouts. How do you take rows and lay them out on a page? So if your rows are all of fixed size, we talked about a couple of different ways of laying them out on disk, either packing them together in one contiguous region or spreading them out all over a page of disk, or by using a header block that stored a bunch of pointers, or actually footer block, excuse me, that had a bunch of pointers that pointed to the start of each record or row on the page. And then we talked about a couple of different ways that you could organize pages together. Okay, we also talked about indexes. So an index is a way of getting at your data more quickly if you know something, well, it's a way of exploiting the organizational structure of the data to get at your data more efficiently. So kind of the big index structure that we talked about, or most of the big index structures we talked about were tree indexes, where you essentially used a set of nodes that could partition the space of the data below them. Every node in the tree essentially splits all of the data in half. One major distinction I want to make sure I make is between primary and secondary indexes, which are also sometimes referred to as clustered or unclustered indexes. Primary index actually points to the full data. So if I've got a relation R, A, B, C, D, E, 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 1, 2, 2, 1, then a primary index would store 1, 1, 1, 1, 1, 1, 1, 2, 2, 2, 2, 1, 2, 2, 1. The primary index would actually organize all of this. So if I was sorting, let's say, by A, then I'd have a set of nodes that point to the A's of 2, a set of nodes that point to the A's of 1. But the main thing is that the data here is that the data is actually either organized in conjunction with the index or actually part of the index structure itself. Meanwhile, a secondary index or an unclustered index, let's say on C, let's say on E. Let's give some labels here. Let's call this page 1, page 2, page 3. So an index on E, again, you'd have a split of 1 and 2, and 1 and 1. Here you have, rather than having the data explicitly part of the index or explicitly even organized along with the index, you have instead pointers to where the data is located. This pointer can either be some sort of primary key, or it can be an actual location either in memory or on disk. In this case, I might point to page 1, which is the first tuple where E is 1. Page 3 is the second tuple where E is 1, and page 2 is the page where E is 2. So primary and secondary. Clustered because all of the data is organized. Clustered, all of the data with the same or similar keys is clustered together. All right, questions so far? All right, we talked about a couple of different indexing strategies. The big ones, or the two big categories being tree and hash indexing. Trees have, where there's a tree, there's a log. Trees have logarithmic lookup times and logarithmic insertion times. Hash tables have constant lookup times. We talked about static hash indexes. We also talked about extendable hash indexes, and yeah. Time. All right, let's keep pushing on. Okay, the next, we then also talked about cost estimation. So this is something I'd like to spend a bit of time on. So cost estimation, there's three components to cost: CPU time, I/O time, and memory usage. And all three of those reduce to one specific problem. If you can solve, if you can tell me how many tuples go into each side of an operator and how many tuples come out, then I can tell you essentially how to determine the CPU time, determine the memory utilization, and determine the I/O cost. So the thing I really want to focus on to start with is doing arity estimation. The big thing here is a term called selectivity, which basically is the fraction of the tuples that come through an operator. So in the case of projection, oh, actually, so the projection operator lets through all of the tuples that come in. The selection operator we'll talk about in just a moment. The cross-product operator has inputs coming from both sides, but you can either look at, you can kind of treat it as a unary operator. And the selectivity here is actually going to be bigger. So if I cross anything with a relation R, the selectivity is basically going to be the size of R. For every tuple that comes in the case of projection, one tuple comes out. In the case of cross product, for every tuple that comes in on the left-hand side, R tuples come out on the right-hand side. And union is also 1. The interesting thing here is the selection operator, obviously. And there are two basic types, there are two basic types of selection predicates that we're going to talk about. The first is a selection predicate that applies to a single attribute. So you guys did fairly well on this particular part of the midterm, so I'm not going to spend too much time on it. But again, the key things to remember are that if you have a uniform distribution, equality predicates, you can come up with an exact selectivity. So if I know that there are values, there are n possible values, in the data, and this is a statistic that can be harvested fairly easily, then equality predicate is going to give you 1 over n records, and a comparison is going to give you some fraction of n, where k is the percent of or sorry, not the percent, but the number of values. Could also do histograms, which give you more detailed information about the value, the data. Join predicates are a little more tricky, but you can essentially think of each join predicate as being kind of like a single attribute predicate. So if I've got two relations, R, A, S, B, and I have a join condition, R join on A equals B with S, then one of the ways that I can approach this problem is by looking at every row of R independently. So for one specific row of R, 3, 1, 4, 2, 2, 1. So for one specific row of R, let's add one more. Values from 1 to 4, and there are, what do we have? There are 8 of them, and again, values from 1 to 4, and there are 8 of them. So for every row of R, it's kind of like we're running a selection on S. So if we know, if we look at the first row of R, then we can essentially replace this, the join for that one row of R is basically going to look like select from S, project 1 into A, B, and then select B equals 1, because we're plugging in the value of A. And this is something that we can do exactly in the same way. We come up with, for every row of R, we find the number of B's that have the same value. So in this case, since there are values from 1 to 4, there are 8 values. On average, we'd expect to see 2 of them come out, and the selectivity of the whole thing is going to end up being, let's look at that. The selectivity of this particular predicate ends up being essentially so there's 8 possible values. There's 4. The number of tuples actually doesn't matter. The selectivity of this particular predicate is just going to be 1 over n. So for every row of R, we have a 1 over n selectivity on S. And that brings me to the one somewhat more difficult part of arity estimation, which is what happens when you have 2 separate predicates. So that particular predicate is 1 over n, and since it repeats for every single R, there's essentially no selectivity on R. You're capturing the selectivity of the joined predicate in that. If I have 2 separate selection predicates, so let's say I've got further, am I still on? Yeah. T with a C, and I would like to find R join on A equals B with S, and then that whole thing joined on B is equal to C here. Then what I care about isn't the total number of tuples at each stage. What I care about is the selectivity of the individual predicates. So, sorry, this is 1 over 4. So I'm still looking at 3, 6. All right, slightly simpler example here. So I've got, let's say, 2 values in T, 1 and 4. As before, I have a min of 1 and a max of 4, which means on average, I'd expect to see in a selection of a selection on C is equal to some constant between 1 and 4. I'd expect to see this thing having a selectivity of 1/4. So as before, this has a selectivity of 1/4. This has a selectivity of 1/4. And what I'm looking at then is the full, that selectivity applied to the full cross product of all of the relations. So in effect, got R cross S cross T. 4 rows on the left, 8 rows on the right, 2 to the second plus 2, times 2 to the third, 2 to the fifth, which is 32. 32 rows in R cross S, and then if I cross that with the 2 rows in T, I get 64. So 64 rows in the overall output of the cross product, and this is going to remove 1/4 of the tuples. This is going to remove 1/4 of the tuples. So I'll end up with 1/16 of the overall number of tuples that I started with in the full cross product. And 1/16 of 64 is 4. 1/16 of the rows times 64 rows is going to end up being an expected 4 rows in the output. Okay, questions so far? Yeah?
For selectivity of cross product, the same as the selectivity of one of the values from R.
So that, all right, that's not entirely true. Yes, essentially you, There are 2 ways to approach the problem. The first way is to just look at all of the selection operators, treating joins as effectively a selection on top of a cross product. So you take the selection operators, equivalence says you can always take the selection operators, migrate them to the top. Basically at that point what you're trying to do is find the probability or the chance or the fraction of the tuples that selection operator is going to eliminate. And the other part, you've got a big cross product of a bunch of things. That's going to compute the number of tuples that you have in total. Treat those 2 as separate things, basically, is what I'm saying. Compute the number of tuples that you start with, compute the number of tuples that you get filtered out, and then multiply those 2 to get the total number of tuples that you expect to get. Any other questions? Okay, there's one other comment I'm going to bring up, which is that there is one other case where you can get the selectivity even more precisely, and that's when you have a foreign key constraint. So a foreign key constraint is always doing a foreign key lookup will always give you exactly 1 tuple for obvious reasons. If you're looking up a key, well, you're getting back exactly 1 tuple. All right, where are we? Oh, so this isn't actually required for the exam, but there's also a general rule of thumb that works 90% of the time. And I'm pulling 90% out of somewhere. The databases since the dawn of time have basically used 10% as a rule of thumb. If you can't figure out what the selectivity is, 10% is neither too low nor too high, and it actually seems to work quite well in a lot of cases. Not important for the exam, but just a general rule of thumb that might come in handy. All right, so once you have the arity estimated, then it becomes a lot easier to estimate I/O. You can attribute the amount of work that, the amount of I/O that each operation needs to perform. So we talked about, and I don't have time to go over each of these, but we talked about the cost of each join algorithm with respect to the number of tuples coming in. Sort, obviously n log n. Table scans, well, you have to read the whole table in, so however big the table is, that whole thing has to be read in. Index scan actually uses the selectivity, so if you're looking for values that satisfy some specific predicate, and the index is actually going to do a reasonable job of responding to that predicate, then modulo kind of an initial setup cost, usually something like log n for trees, for tree indexes, and O1 for hash indexes, then in general, the responding to the predicate is just going to require a linear scan of the data. So what you're looking at, the cost of an index scan is usually going to be proportional to the number of tuples that pass the predicate, not the number of tuples in the relation itself. Questions so far? Okay, I might actually make this. Memory estimation. We also talked about estimating memory in each algorithm. Project, select, union don't actually require any memory. Most joins do require more than a constant amount of memory. The one exception being being sort merge join. At least the merge phase of sort merge join. But everything else requires more than a constant small amount of memory. I refer you to the textbook and the slides. There's a couple of tables in pretty much every lecture that talks about this that give you that lookup, and I'll include a lookup table on the exam as well. Right. Okay. Any questions about cost estimation before I move on?
For merge join requires a constant amount of memory
For the merge phase.
for the merge phase.
Yeah.
And then every other join requires not.
The amount of memory required varies. So nested, let me retract that. Nested loop join also requires a constant amount of memory, but is hideously inefficient. So, yeah. Block nested loop join requires an amount of memory proportional to the block size. Hash one pass or in-memory hash join, obviously you're keeping all of the data for at least one relation in memory. External hash join requires enough memory to load in one bucket from each relation. So if you have n buckets, on average you need 1 over n times the size of both relations memory. Index nested loop join requires whatever memory requirements the index has. Again, depending on how you treat the index itself, that could potentially be viewed as having a constant amount of memory, but that's not realistic. So index nested loop join has whatever the memory cost of the index. What am I missing? And then, yeah, sort merge join. Obviously, sorting requires more than a small fixed amount of memory. But the merge phase, in the extreme, you only need to be looking at one tuple at a time from each relation. Obviously, you might want to do a little bit of buffering, but there's no requirement. Okay. Any other questions? This is a good question. All right, moving on. Transactions. Two basic concepts are serializability and equivalence. Serial schedules and equivalents. A serial schedule is, well, let me start off with the basic transaction semantics. Our goal is to allow some piece of code to modify the data in a way that that transaction thinks it's the only transaction running at any given point in time, which means that any of its write operations, any changes it makes to the data, any data it reads from the database, it should retain the illusion that it's the only thing running. You should be able to create a scenario where the transaction, the behavior of the transaction depends on the behavior should be able to depend on it being the only thing running at a time. So to start off our discussion of transactional, back up. What we'd like to do ideally is be able to interleave the read and write operations for the transaction without necessarily breaking that illusion. So in order to kind of think about what it means for an interleaving of read and write operations to be correct, we start by thinking of the simplest possible correct case, which is you take the transactions and you order them however you like, but you allow each transaction to run to completion before starting the next one. Doing everything for transaction 1, then everything for transaction 2 is just as correct as doing everything for transaction 2, then everything for transaction 1. What is potentially incorrect is if we do some things for transaction 1, some things for transaction 2, finish off 1, finish off 2. But OK, so we start off with this base case, everything for one transaction at a time. This is a serial schedule. And then we looked at a couple of different definitions of equivalence. And two schedules are equivalent if they satisfy some properties. The basic definition of equivalence is to look at the output. Execute the schedules to completion, look at the output, and if everything that got read out and everything that's in the output is identical, then they're equivalent. Of course, executing a serial schedule to completion doesn't actually help us if we want to interleave things. So instead, there are a couple of lighter weight definitions that we talked about, conflict serializability and view serializability. Conflict serializability was that we were allowed to reorder two operations in different transactions as long as those two operations were either both reads or both applied to different objects. So we're allowed to, so read on A is equivalent to read A. Write B is then write A is equivalent to write B after writing A. But write A and write A is not equivalent to writing A after writing A. So you're allowed to reorder two operations if they're applied to different objects or if they're both reads. And if you can take the schedule and through a set of rewrites that follow these rules, reach a serial schedule, then the original schedule is serializable, or more specifically, conflict serializable. View serializability is a slightly more general idea, and that basically says that all we really care about is the output. So if I also have a third transaction that writes to A, and that third transaction obscures the write to A, and more importantly, nothing else reads that A in the meantime, then it's okay. Then from the perspective of the outside world, it doesn't matter which order those writes were applied in, because something else came along and undid it anyway. Now, two schedules that follow that particular set of semantics are called view serializable. Okay, we talked about a couple of different specific implementations of concurrency control. We talked about using locks. I wanted to talk about hierarchical locking, but don't think I have time. So we talked about hierarchical locking really quickly, just the observation that you could have there are some operations that you want to apply to an entire table. There are some operations that you want to apply to individual rows. And if you have two small operations, each manipulating a separate set of rows, you want those two sets of operations to be able to work concurrently. Meanwhile, if you have a really big operation that affects the entire table, you don't want to slow that transaction down, taking locks on every single row in the table. So instead, we have this notion of hierarchical locking, where we put little signal markers, or where we create a hierarchy out of the objects in the database, starting from the entire database, then going to tables, then pages in the table, then rows in the pages. And if a transaction wants to take a lock on one or more of these objects, it starts at the root, and it places little breadcrumbs, intent locks, that follow it all the way down to whatever level it actually does want to lock. And those little breadcrumbs allow higher level, allow transactions that want to lock a coarser level of the database to see what's going on and to make sure that to see what's going on and to avoid stepping on the lower level transactions' toes. We also talked about two-phase locking as a way to avoid deadlocks and ensure or enforce conflict serializability. We also talked about optimistic concurrency control, which was the idea of allowing each database, each transaction to work in its own hidden invisible world. So there's a read phase where the transaction does what it needs to do, but all of its writes are cached or buffered or hidden from the rest of the world. Kind of like what you're doing with Git. If you're editing code on your local machine, that's basically the read phase. Then there's a validation step where the system takes a look to see whether any of the operations that you've performed, the transaction has performed, conflict with anything else that has been committed since the transaction was started. If there are any conflicts, it forces an abort, and if not, it moves to the write phase, where all of those buffered writes become visible to the rest of the world. So validate plus write is essentially what you do, what you get by doing git commit and git push. Well, as one thing. We also talked about timestamp concurrency control, which is a way of using markers on every single object to see whether any markers on every single object to avoid conflicts. I'll note timestamp concurrency control is typically one of the few cases of actual view serializability. Okay, moving on. Logging. We talked about logging. So the state of the database, basically, you've got the portion of the database sitting on disk. You've got some portion of the database that is sitting in memory, so buffer, some portion of the database that is sitting on disk, some portion that's sitting in memory, and all of the operations in the database interact with the buffer. There's also a log. The transactions interact. Every time a transaction does something, it puts some information into the log, and eventually the log gets flushed to disk. Once the log is safely on disk, that is the point where the information can be considered to be safely recorded on disk. Even if changes to the buffer haven't been flushed back out to disk, as long as it's in the log and as long as that portion of the log is safely on disk, it doesn't matter whether the buffer has been also flushed to disk. And that allows the database to be a little more efficient. So we talked about redo logging. Which basically allows us to recover the state of the buffer and the disk if the system crashes at some point during processing. We also talked about undo logging. Which allows us to revert aborted transactions. And the final thing we talked about was the Aries protocol for recovering from a failure. And the protocol basically consists of 3 phases: analyze, redo, and undo. In the analyze phase, you recover the in-memory state. And that basically means the buffer, not the buffer, that means the transaction table and actually that's the main thing. The redo phase, you recover the buffer. And then in the undo phase, you revert any transactions that were still pending at the time of the crash. So the analyze, you go back through the log, you find all of the records in the log that signal that a transaction has changed state or that a transaction has entered into the system. The redo phase, you go back to the first operation for any given transaction that is currently active in the system, and you replay that. And then in the undo phase, you go backwards through the log and use the undo log entries to revert any changes from transactions that are still pending. We also talked about parallelism. Since that was the last 3 lectures, I'm going to skip that, but that's also going to be relevant. Final questions? Yeah?
Can you post the midterm 1 solutions on Piazza, please?
They're not already posted?
I'm looking at it right now. I see midterm 2 and that's it.
Okay, sorry about that. I will post them. This? Yeah, so Just for reference, I've been building notes for myself for kind of what to cover and general concepts. They are attached to all of the like in-person slides. Anytime you see slides like this, there's one of these at the end.